I'm very excited to have like everyone here. If you do need like anything, like just let me know. I'm just gonna go over a few slides over here so that like we can just like show like what we do here at Loop. So for today's event, like we're this Run the Ruby event. Foods and drinks are sponsored by us, and like like if you do need more, just let me know. Cause like like we're almost like running out, but like we do have like more drinks and like over there, and like I can like order some for pizzas, and then washrooms are right over there. I think like some people were already able to find like the washroom, and I hope you have like fun today and enjoy and like meet new people. Okay. So just about Loop. Loop is a fast-growing fintech startup that enables businesses to seamlessly manage money around the world, so our clients can access more markets, accelerate their growth, and simplify their operations with the only truly cross-border banking platform. So we're a cross-border banking platform. What that means is that we offer financial services to businesses here in Canada, and hopefully we'll expand like more and like internationally. But yeah, like we help them like if like for example if you have a credit card here, our credit cards actually work in a multi-currency way. So like we have credit cards that has like you just have a single credit card that has a USD that can work with USD, CAD, Euro, and GBP. And imagine if like if you're spending in USD, you pay us back in USD. If you're spending in Euro, you pay us back in Euro. Because some of the businesses right now, they're not operating anymore just in Canada. They're operating internationally. So it makes sense like for them like just to pay us back in the currency that they're earning, so you don't have to deal with foreign exchange. So just want to share that like with you. So yeah, Loop like we're doing like the next generations for business banking. And who we are, like, so I'm the head of engineering here at Loop. So like our stack is in Ruby on Rails for our backend, so our API is in Ruby on Rails. Our frontend is in React, and we have like a Django for our underwriting services here in the company. So if you know any of those languages, please feel free to talk to me later tonight, because like yeah, like we are hiring for a senior software developer here in the company, and yeah, like. That's about it. I also have like our previous like CDO like here in Loop, and Brandon who started like another like company. He's also part of our board like here at Loop, but like I want him like to share something about his company.
Thanks, Carmen. I just wanted to share that we're also hiring a senior software engineer, Rails backend, React frontend. Our company, Mangrove Systems, we basically help companies track the CO2 that they inject underground. So if climate is of interest to you, we're working with some of the largest carbon storage projects in the world, around the world. So yeah, if you know data, Rails, and have a little bit of front-end spice to you, that would be amazing. Come talk to me later. Thank you, though.
Okay. Yep. And yeah, thanks for joining us today. And that's about like our plug for hosting for our company. And I hope I can talk to some of you like later. So yeah, thank you. Like the switch, there's only one switch in the entire room. So if we switch like when you run this, if we switch this, we should switch our entire server system. What? Yeah, so there's no switch.
It's a CR test.
Hey everyone, I'm Peter. I'm on the Ruby core team, and I'm a senior developer at Shopify on the Ruby infrastructure team. In this talk, I'll be talking about configuration and tuning you can do to optimize Ruby's garbage collector for your Rails app. So you can find these slides at this URL or at this QR code, and I'll leave this URL up for a few slides so you don't need to frantically try to get this URL. So first I'll introduce myself. I'm from Ottawa and I'm currently based in Toronto. I'm a senior developer at Shopify on the Ruby infrastructure team, where I work on performance of the Ruby programming language. I'm a Ruby core committer, and I'm the co-author of this feature in Ruby called variable width allocation, which I will talk about in this talk. This feature was introduced in Ruby 3.2 and improves the performance of Ruby through better memory management. I'm also the author of a tool called Ruby Memcheck, which is a tool used to find memory leaks in native gems. This has found memory leaks in popular native gems such as Nokogiri, Liquid C, and gRPC. I'm the author of a gem called AutoTuner, which is a tool that helps you tune the garbage collector for your Rails app. And I will introduce this gem in this talk. I'm also a photography geek, so feel free to talk to me about cameras and follow me on Instagram at peterzoo.photos. So first, I'll talk a little bit about what a garbage collector is. So contrary to the name, garbage collectors are not just responsible for reclaiming dead objects. They're responsible for the whole life cycle of objects. So garbage collectors are responsible for allocating memory when the object is first created and recycling that memory when the object dies. So the garbage collector is also responsible for determining when an object is no longer alive. It does this by keeping track of lifetimes of objects. There are various techniques to do this, such as reference counting or marking. Ruby uses the marking garbage collector, and I'll talk a little bit about what that means later on in the talk. Ruby is a garbage collected language, and that means that you don't need to worry about allocating memory when you create objects and freeing the memory when you're done using it. So let's take a closer look at what Ruby objects are under the hood. So every Ruby object lives in this thing called a slot, which is a region of memory allocated for the object. These slots are acquired from the garbage collector, and we'll soon see how this acquisition happens. So these slots are of a fixed size and cannot be resized. So sometimes we need to allocate more memory than what the slot offers, and we'll have to allocate that memory externally, such as through the system using malloc. So the garbage collector doesn't allocate slots individually from the system. Slots live in what's called a page. Because allocating each slot individually is bad for performance, so we allocate memory from the system in units of heap pages. Heap pages in Ruby are 64 kilobytes in size, and all of the slots in a page are of the same size. This is done for simplicity and to avoid external fragmentation. External fragmentation is when the allocation of small-sized objects between large objects causes small gaps. And when these small objects are reclaimed, that memory cannot be later reused by larger objects, which increases memory usage. So Ruby 3.2 introduced this new feature called variable width allocation. This feature allowed the allocation of dynamic-sized objects through the garbage collector. Prior to this feature, all slots in Ruby were 40 bytes in size. So every single object in Ruby occupied a 40-byte region of memory in the garbage collector. So this meant that objects that needed to allocate more memory would have to allocate it externally through the system, such as through malloc. This was bad for memory efficiency, and this was bad for performance. So variable width allocation enabled dynamic-sized allocations through the garbage collector, and it introduced this new concept called size pools. Each size pool holds a collection of pages, and every page in a size pool contains the same slot size. And there are currently 5 size pools in Ruby: 40, 80, 160, 320, and 640 bytes in size. These numbers were chosen for the best balance of memory efficiency and performance. So let's recap the data structures we've discussed so far. First, we have a single slot, which is used to hold the data for a single object. These slots live in pages, and there are many pages in the system, each with varying slot sizes. And pages with the same slot size lives in the same size pool. So 4 size pools are illustrated here due to slide space constraints, but there's actually 5 size pools in Ruby. So we've just seen the data structures inside of the garbage collector. Now let's talk a little bit about how objects themselves are allocated. So each heap page has a linked list of slots that are empty, and this is called the free list. To allocate an object, we pop an element from this free list. So here's an illustration about how object allocation works. So here's a heap page with a few objects allocated, And we have a free list that links all of the free slots on this page. So let's try to allocate this new object that is a regex. So we simply allocate this object onto the head of the free list and move the free list to the next element. And we can keep on allocating objects until we run out of free slots. And at this point, if we don't have more pages with a free list, we must either allocate a new page or we must run a garbage collection cycle to free up slots. So let's take a look at what happens when Ruby's garbage collector runs. So as I've mentioned before, Ruby uses a mark and sweep garbage collector. And as the name implies, it has two phases. We first start off in the mark phase. This is when we traverse the object graph and mark the objects that we traverse. And then in the sweeping phase, all of the objects that are unmarked are dead and can be reclaimed by the garbage collector. There's technically a phase in between of marking and sweeping called the compaction phase. But note that compaction is not enabled by default. If enabled, compaction moves objects around in the Ruby heap to reduce fragmentation. This can reduce memory usage and increase runtime performance. It's also important to note that Ruby uses what's called a stop the world garbage collector. This means that all execution of Ruby code is paused while the garbage collector runs. This simplifies the implementation of the garbage collector, avoids the need to perform a synchronization between threads, and avoids the possibility of race conditions inside of the garbage collector. However, this means that the longer the garbage collector takes to run, the longer your application will be paused. So in a Rails app, if the garbage collector runs during a request, this can mean that your request takes much longer to execute than normal. So we start the garbage collector with the marking phase. This is the phase where we determine what objects are alive by traversing the object graphs, by reading the references of objects using a breadth-first traversal algorithm. For example, for an array, the references will be the contents of the array. For a hash, the references will be the keys and the values of the hash. And for an object, the references will be the instance variables of the object. Ruby uses three colors to mark objects. All objects are initially white, which means that the object is unmarked. When we mark an object, we color it as gray. This means that the object has been marked, but the references have not yet been traversed. Remember, we're using a breadth-first traversal algorithm, so we do not immediately inspect the references of the objects that we mark. Later on, we traverse the references of the gray objects, we color it as black. And at the end of the marking phase, all unmarked objects are no longer reachable and can be reclaimed by the garbage collector in the sweeping phase. So here's an example of a Ruby heap with several objects. Object references here are shown using arrows. For example, object A refers to object F, which refers to object I. So we start marking from the list of root objects. This includes objects on the stack, global variables, and top-level constants. We then color the references of the root objects as gray, since we visited them but have not yet visited the references. So then we pick a gray object to visit, and here let's pick object A and visit its references. This colors objects A as black, and we traverse the one reference, which is object F, which we color as gray. So then we repeat for the next gray object, which is object B, and object B refers to two objects, objects G and objects H, which we color both of them as gray. And then we inspect object C, and it has one reference, which is object H, but it is already marked gray, so we do nothing. We then inspect object F, which has one reference, object I, and then object G, and then object H, and finally object I. Now that we have no more gray objects, every object that is colored black is a live object, and every object that is colored white is dead, and can be reclaimed by the garbage collector in the sweeping phase. So we see here that object D and object E were never traversed, and they remain white. So they are dead objects and will be reclaimed by the garbage collector. But there's more complexity to the marking phase. Ruby uses what's called a generational garbage collector. Generational garbage collectors are based on the generational hypothesis, which states that objects either live for a very short period of time or live for very long and are immortal. So in a Rails app, most objects that are created at boot are basically immortal. These are things like your classes, your constants, and your database connections. So then during requests, all objects that are allocated in the request usually live for very short, or even as short as only for that request. These are things like your active model objects, your logging entries, and your other objects to help serve your request. So your Rails app basically doesn't have anything that lives for like a medium amount of time. Everything's either immortal or live for a very short period of time. So in a generational garbage collector, we create new objects in the young generation. And then for objects that survive a while, and in Ruby it's 3 garbage collection cycles, they get promoted to the old generation. We take advantage of the generational garbage collector by splitting marking into 2 types. So we have the minor garbage collection cycle, which marks only the young objects and assumes all of the old objects are already marked. So this can make garbage collection cycles much faster because of the significantly fewer objects that get marked. And because of the generational hypothesis, we should be able to reclaim a large portion of the objects allocated, but sometimes we still need to reclaim old objects. And major garbage collection cycles marks both the young and the old objects. But major garbage collection cycles can often take as much as 10 or 20 times longer than a minor garbage collection cycle, so it should be avoided in a Rails app. Here's an example of a minor marking phase using the same heap but with generations. So some of the objects here are young and some of them are old. And remember, in the minor garbage collection cycle, we assume that all old objects are marked. So we start by marking all of the old objects as black. Note that object E here is a dead object, but because it is old, it is marked. So we won't be able to reclaim it in this minor garbage collection cycle, even though it is a dead object. So then we mark like usual, starting from the root objects. We mark the root objects as gray, and we traverse the references of object A, but since object F is already marked, it's already colored black, so we don't mark it again. So we don't inspect it. We then traverse the references of object B, which is objects G and objects H, but then we don't do anything for object H because it is already colored black. And finally, we color object G black. So in a minor garbage collection cycle, we marked 3 young objects and skipped over 4 old objects. This reduced the number of objects marked and should improve performance. However, the only white object left is object D. So later during sweeping, we can only reclaim object D. Object E is an old object, so we'll need to perform a major garbage collection cycle in order to reclaim it. But there's more complexity. I just showed you how Ruby's garbage collector takes advantage of generations to implement minor garbage collection cycles, but I left out a few critical implementation details. During runtime, we can add a reference from an old object to a young object. But because old objects are not traversed during minor garbage collection cycles, the young object will not be marked. So it will remain white throughout marking. So then it will appear to be dead to the garbage collector. And this will be a terrible bug because now the old object will refer to a reclaimed object by the garbage collector. And so if we ever try to read this young object, we'll either crash or we'll get a completely different object that was allocated into that slot. This is solved using this thing called write barriers. Write barriers are callbacks to let the garbage collector know whenever you add a new reference to an object. For references to objects of the same age, the garbage collector does nothing. The write barrier does nothing. And for references from old objects to young objects, the write barrier places the old object in this thing called the remember set. And the remember set is a list of objects that is traversed during minor garbage collection cycles. However, write barriers are not actually required, and there are some types in Ruby and some native extensions that do not support write barriers. Types that support write barriers are called write barrier protected, and types that do not support write barriers are called write barrier unprotected. So what do we do about these write barrier unprotected objects? Since they don't support write barriers, we won't know when a reference is added to a write barrier unprotected objects. This is solved by always placing the write barrier unprotected object in the remember set. And since objects in the remember set is marked in every minor garbage collection cycle, we lose the benefits of the generational garbage collector for write barrier unprotected objects. So let's look at an example where we have an old object that refers to a young object and a write barrier unprotected object. Note that the write barrier unprotected object is neither old nor young because it does not participate in the generational garbage collector. We introduced this concept called remember set, which is part of the list of root objects. So the write barrier would add object F to the remember set because object A is old and that should say young, by the way. That's a typo. But object F would be young, and so object F would be added to the remember set. So in a minor garbage collection cycle, we first color every old object as black. However, every object referenced from the remember set would be colored gray, so we can inspect the references. Oh, sorry, that was a mistake. So object I here is the one reference. So object F, yeah, right. So we put object F in the remember set because it is the old object that refers to a young object. That's why object F is in the remember set. So then we pick object F to mark, and that would mean that object I gets marked. And then we mark object H, and then object I, and finally object J. So we've just seen how the marking phase in the Ruby's garbage collector works. We've now determined the liveliness of every object in the garbage collector. So all unmarked objects are dead. And the sweeping phase reclaims the resources of these dead objects. In addition to reclaiming the slot for the dead object, we also free any externally allocated memory and other resources such as closing file descriptor, closing sockets, or terminating threads. Here's an example of the sweeping phase using an example with two heap pages. Marked objects here are shown in black and unmarked objects here are shown in white. We sweep by inspecting one object at a time. We first inspect object A, but because it is a marked object, we skip it and do nothing. Object B here is not marked, so we reclaim it, and now we're left with an empty slot that we can allocate new objects into. And then we can keep repeating for the rest of the slots on this page. Well, okay, so this is an empty slot, so we do nothing and we skip it. So we do the sweeping for the rest of the slots on this page. And after we're done with sweeping this page, we move on to the next page and we repeat this process. So now that we're done with the sweeping phase, there is a phase in between of marking and sweeping called the compaction phase. And the compaction phase reduces fragmentation in the Ruby heap by moving objects that all live objects are adjacent to one another. This can decrease memory usage and improve performance. This can save memory because there will now be more completely empty heap pages, which can be released back to the system by the garbage collector. If you're using a forking web server such as Puma or Unicorn, this can reduce the amount of copy on write. And this will decrease the amount of memory used by your Rails app. It can also improve runtime performance through better CPU cache locality, and can also speed up garbage collection cycles. Variable width allocation takes advantage of the compaction phase to move objects to their optimal size, because objects can change size during runtime. So this can further help decrease memory usage and improve runtime performance. It's important to note that compaction is not enabled by default. And to manually run compaction, you call gc.compact or set gc.autocompact to true. Autocompaction runs on every major garbage collection cycle. So I don't really have time to give an example about how compaction works, but that was a quick introduction on how the garbage collector works in Ruby. If you want a more in-depth article about how the garbage collector works, check out my blog post at this link. So we've just seen how the garbage collector works from the inside, and now let's apply this knowledge and see how we can collect metrics from the garbage collector so that you can tune the Rails app you can tune the garbage collector for your Rails app. So you can't really see this, but the method to get statistics from the garbage collector is this method called gc.stat. I wonder if I can give a live demo, which would be a terrible idea.
We can't really see the screen anyway.
Well, let me pop it. Alright, maybe that will work.
Love it.
Alright, maybe that will. So, gc.stat gives us some information. So it returns a hash, and it gives us information such as, first we have count here. We see 19, if you can sort of see that, which is the total number of garbage collection cycles ran. And we want to minimize this number because more garbage collection cycles means more and possibly longer pauses during requests. We certainly don't want to run more than one garbage collection cycle per request because very little objects will be dead during a request. So the additional garbage collection cycles will not be doing much. We also see the total time in milliseconds spent inside of the garbage collector. Using this information, we can determine actually, I think I'm on 3.2, which I do not want to be in because there is a There we go. All right. So on new in Ruby 3.3, we've got, so in addition to time, which is the number of milliseconds spent inside of the garbage collector, we now have marking time and sweeping time split. So we know how much time is spent in each of these two phases. And here we see we spent 10 milliseconds in marking and 4 milliseconds in sweeping, giving us a total of 14 milliseconds inside of the garbage collector. So using this information, you can determine the proportion of time spent inside of each of the phases. And using this information, you can also determine the proportion of time spent inside of the garbage collector per request. And this is useful because if this proportion is high, it means that tuning the garbage collector will likely give you good improvements in response times, whereas if this proportion is low, then it might not be worth your effort to try to tune the garbage collector for your Rails app.
Peter, at a high level, how would you do that? How would you determine the amount of time in the garbage collector during your request?
Yeah, so that's a great question. So this time gives you the cumulative amount of time spent inside of the garbage collector since boot up. So then what we do is we get this number before you do your request, run your request, and then using that you can also figure out how long your request took, and then if you do the amount of time after the GC stat time of after minus the GC stat time of the before you did your request, then you know how much time you spent inside the garbage collector, and you also know how much time you spent inside the request. And then if you just divide that, then you'll know the proportion of time spent inside of the garbage collector for that request. Does that make sense?
Yeah.
When you do the request, it's not only about the garbage collector. You have to get all the data and process the model and fetch all necessary data from the table. It's not only about the garbage collector process.
Right.
It's actually the time you spend to perform the request. It's not only about the garbage collector.
Yes. Yeah.
It's
Yeah.
still not clear how you get this.
With a 1 second request, it's spending 500 milliseconds in garbage collection. So there's lots of things wrong there, but that's a sign that something about the garbage collector could be going wrong.
Yeah. So if let's say you're looking at extremes like P99, P99.9 response times. And let's say your response time is 2 seconds. And of the 2 seconds, you spend 1 second in the garbage collector. Then you know if you can tune the garbage collector so that you can have your P99 response times. If you tune the garbage collector well enough so that, if the garbage collector time becomes negligible, then you know that you can significantly reduce your P99 response times. But if, let's say, your P99 response time is 2 seconds, but you spend 20 milliseconds in the garbage collector, even if you reduce that to 0, it's not even going to make a dent. So you have to look elsewhere. Maybe your database is slow. Maybe you have bad SQL queries. Maybe you're calling some sort of external service in your thing that could be moved into a background job, for example. So this is like a quick way to figure out, is it worth it to tune the garbage collector? Or should you even put in the effort? Does that make sense? So here we see this thing called heap allocated pages, and that's the total number of pages allocated inside of the garbage collector. And the number of pages allocated almost always directly correlates with the amount of memory your Rails app uses. But sometimes increasing the number of pages can decrease the frequency of the garbage collector because you have more buffer before a garbage collection cycle has to run. And so it's sometimes a trade-off of using a little bit more memory for better performance. And here, let me move this down a little bit. Further down. So we see this key called heap live slots. And this is the number of objects that are currently alive in the system. And we see in this IRB instance, there's about 50,000 objects that are currently alive. And we see this key called heap free slots, which are the number of slots that are free and can have objects allocated into them. And we see about 11,000 free slots. So when the number of free slots reaches 0, we are guaranteed to have to run a garbage collection cycle in order to free up slots, so we can allocate more objects. But the garbage collector may run due to various other reasons, not just when this number reaches 0. So where am I at? Where's my cursor? Here we go. So here we see total allocated objects, and this is the cumulative number of objects we've allocated since the boot up of Ruby. So this number only ever goes up, never goes down. So using this number, you can determine the number of objects allocated per request. You just have to get this number before the request, and then get the number after the request, calculate the difference, and you know exactly how many objects were allocated per request. And here we see that there's about 21,000 objects allocated since the boot up of this IRB session. So you can use this to determine what controllers are allocating too many objects, and maybe you can use that to find optimizations to trim down the number of allocations you do in a particular controller. Yeah. So then we see, let me go down a little bit. We see the number of minor garbage collection cycles, and we see we have 17 minor garbage collection cycles, and the number of major garbage collection cycles ran since the boot up of Ruby. In a Rails app, you want to mostly run minor garbage collection cycles, and so if you're running a lot of major garbage collection cycles, then that is a sign that you should tune the garbage collector so that it runs less of those, because the major garbage collection cycles marks all of the objects, so it often takes a significantly more amount of time to run a major garbage collection cycle than a minor garbage collection cycle. we also see the number of compaction cycles we ran. It's 0 here because it's not enabled by default, so it doesn't get run. There we go. Oh, well, I can't scroll any further. But we also have the number of old objects here, and there's about 37,000 old objects currently alive in the system. And remember, because of the generational garbage collector, objects that are old are only marked during major garbage collection cycles, and the young objects are marked during both major and minor garbage collection cycles. All right. So one more. All right. So, there we go. All right, I don't know what I typed last time. So new in Ruby 3.2 is this method called gc.stat_heap. And this was introduced for variable width allocation. And this provides statistics inside each of the size pools in the system. So we get a doubly nested hash from a gc.stat_heap, where the key of the top level hash is the size pool name, and its indexes 0, 1, 2, 3, and 4. So there's 5 size pools. And then these keys point to another hash inside that contains the statistics for that particular size pool. So for this size pool, we see that size pool 0 has slot size 40 bytes. And we see the number of pages inside of this in this size pool here. Even pages with 26 pages inside the 40 byte size pools, which corresponds to 42,000 slots. So using this number, the number of pages and the number of slots, we can determine the distribution of object sizes inside of your system. We also see the number of major garbage collection cycles forced by the size pool. And if this number is too high, then it means that the size pool is likely too small, and increasing the size would likely improve performance, which I will talk about later on. All right, I think I can move back. Oh, I don't want to play the animations. So we've just seen how to collect and interpret metrics from the garbage collector. So now we'll look at some of the tuning to help personalize the garbage collector for your Rails app, and how to improve performance using the information we've gathered so far. So this one's pretty obvious. If you allocate less objects, there's less pressure on the garbage collector, so the garbage collector runs less frequently. Less objects allocated means there's less objects to mark during the marking phase, and less objects to reclaim during the sleeping phase, so the garbage collector just runs much faster. Strategy here is to find controllers that allocate lots of objects and try to find optimizations to help trim these allocations. If you reduce the number of times the garbage collector runs, then we theoretically spend less time in the garbage collector. Specifically, we want to decrease the number of major garbage collection cycles, because they can take often as much as 10 or 20 times longer to run than a minor garbage collection cycle. So how do we reduce the number of major garbage collection cycles? So this environment variable reduces garbage collection cycles at boot by using the Ruby GC heap init slot environment variable. This sets the initial number of slots in the garbage collector, so the garbage collector does not have to grow the heap at boot. And so instead, the heap will be immediately grown to that size. You can determine good values for this environment variable by measuring the number of slots in the heap after your app has reached peak performance in production. Note that if this value is too high, then your app could use significantly more memory. Another environment variable to tune is the GC oldmalloc limit and limit max environment variable, which determines the amount of memory allocations before a major garbage collection cycle is RAM. The default is 128 megabytes for the max. At Shopify, we set this environment variable to an extremely large number to essentially turn it off. This may increase the amount of memory used, but we saw a significant performance improvement. Another technique we use at Shopify is called the out-of-band garbage collector. This runs the garbage collector in between requests while the Rails app is idle. Ideally, the garbage collector never has to run during a request. But this technique is challenging to implement for threaded web servers such as Puma with multiple threads, because we do not know what the other threads are doing, and we cannot control the other threads. Remember, Ruby's garbage collector stopped the world, so running the out-of-band garbage collector on one thread could cause the other threads to stall. So one technique to get around this would be to synchronize all of the threads to make sure they are all not serving the request before running an out-of-band garbage collector. But this would further decrease capacity, as multiple threads could be stalling an indefinite amount of time to wait for a slow thread to finish serving the request. So it's recommended to only use the out-of-band garbage collector for forking web servers, such as Unicorn or Puma on clustered mode. The out-of-band garbage collector is also very, very tricky to implement, because we cannot look into the future to determine when the garbage collector will be ran. So we have to use heuristics to predict when the garbage collector will be ran. Unfortunately, if we run the garbage collector too aggressively, we'll have long periods of stalling in between requests, and this would decrease capacity as we spend time doing nothing. And if we don't run the garbage collector frequently enough, it will be ineffective, as we'll still be running the garbage collector during requests. And as you can see, the out-of-band garbage collector is tricky to implement, but it may be worth it if you need to decrease response times, but you're allocating a large number of objects during requests and seeing long pauses inside of the garbage collector. Let's see the impacts of tuning the garbage collector on one of Shopify's highest traffic apps called Storefront Renderer. Storefront Renderer renders the home pages and product pages that buyers interact with on Shopify, so it's very important that this app has fast response times. After tuning the garbage collector, we decrease the average time spent inside of the garbage collector by over 50%, and decrease the 99th percentile time spent in the garbage collector per request by 80%. So how does this translate to response times? Average response times decrease by about 13%, and 99th percentile response times decrease by 25%. This is quite a significant decrease because we still spend quite an amount of time inside of I/O during these requests, such as to database or to caching like Redis or Memcache, and those things cannot be optimized by tuning the garbage collector. So these performance improvements weren't just from tuning the garbage collector. We also analyzed the garbage collector and made improvements that will speed up your Rails app in Ruby 3.3. So this feature adds a new configuration environment variable called the remembered write barrier unprotected objects limit ratio. Oh my God, it's a mouthful. But this calculates the limit for the number of write barrier unprotected objects that are placed in the remember set. When this limit is reached, a major garbage collection cycle is ran. Previously, this limit was calculated as twice the number of write barrier unprotected objects that exist after you run a garbage collection cycle. But if you have very few write barrier unprotected objects after a garbage collection cycle, then this limit would be very low. So major garbage collection cycles get triggered very frequently. So this limit is now calculated as a proportion of the old generation objects that are in your system and defaults to 1%. On Storefront Renderer, this feature improved average time in the garbage collector by about 33% and halved our 99th percentile time in the garbage collector. This translated to a 4% decrease in response times and a 14% decrease in 99th percentile response times. This next feature changed the garbage collector algorithm for references from old generation objects to young generation objects. In the old algorithm, we immediately promoted young objects to an old age. This created many old objects during requests because we sometimes store temporary objects in old objects, such as temporary objects that are placed in a buffer during logging. So if the buffer lives for a very long time, it's likely an old object, but the buffer gets flushed very frequently, so it doesn't make sense to make all of the entries also old generation objects. This new algorithm places the old parent object in the remember set when a reference to a young object is added. This allows the young object to age like normal and only be promoted to the old generation after surviving for a long time. This improved our average time in the garbage collector by 19% and decreased our 99th percentile time in the garbage collector by 12%. This translated to a 4% decrease in average response times and an 8% decrease in 99th percentile response times. You can learn more about these two improvements in Ruby 3.3 in this blog post, where we discuss how these features work and the impacts in greater detail. But there's one more thing I want to talk about. So I've talked about quite a few things in this talk, from a crash course on how the garbage collector works, how to collect metrics on the garbage collector, some ways to tune the garbage collector, and some new garbage collector features in Ruby 3.3. So you might have gotten it, or it might have left you more confused. But there's good news. You can forget it all, because I built the auto-tuner gem. This gem analyzes the garbage collector between requests and provides suggestions to tune the garbage collector for your Rails app. You can find the source code of this gem at github.com/shopify/autotuner. Oops. So setting up is extremely simple. You follow these two steps in the README, and it'll begin emitting garbage collector tuning suggestions. So after you set it up, it will begin emitting tuning suggestions that look like this. It first explains what the tuning suggestion attempts to solve and the impacts on your app. So this particular tuning suggestion will reduce the number of minor garbage collection cycles, which may improve response times, but may also increase memory usage. We see the environment variables next that can be used to apply this suggestion to your Rails app, and advice on how to A/B test this feature on your Rails app. And we'll now talk about how we experiment and compare impacts of garbage collector tuning at Shopify. So initially, all of our servers are untuned, meaning there is no tuning applied. After all the tuning gives a suggestion, we designate a small random portion of servers as the experimental group. If your app has high traffic, this might be something like 5%. If your app has low traffic, this might be something like 30%. The idea here is to keep the group small in the unlikely event that the tuning causes a significant degradation in performance, but big enough to keep to be able to compare results while keeping variance low. So we then apply the tuning suggestion to the experimental group. And then we compare the impacts of the change to the untuned group. So response times fluctuate significantly depending on the type of the request, the load of the web servers, and external factors such as the response times of your database. So it's difficult to measure the impacts of tuning over two separate time intervals. So it's much easier and gives more confidence to compare the performance impact over the same time period. If tuning provided a positive impact on performance, we create a stable tuning group that is similar to the experimental group in size, but only contains tuning that have yielded a positive performance impact. We copy this tuning over and apply it to both groups. We then apply the next tuning suggestion to the experimental group and compare the impact of the tuning suggestion to the stable group. If tuning doesn't provide a positive performance impact or gives a trade-off that you don't want, then we can simply remove it. Sometimes tuning may give a trade-off that we don't want, and the most common ones that we've seen is having better average response times, but making extremes like 99th or 99.9th percentile worse. We then experiment with tuning suggestions one by one in the experimental group, and we keep suggestions that have a positive performance impact by copying it over to the stable group, and remove ones that don't give a positive performance impact. Once we're satisfied with the results of tuning, we'll compare the total impact of the tuning to the untuned group. And once we've gathered enough data, it's finally time to roll out tuning to all servers, and if everything has gone right, you should observe a positive performance impact. So this talk was originally given at Rails World 2023 in Amsterdam, and you can find a recording of this talk at this URL. You can find the slides of this talk at this QR code. Please check out this gem at this URL. Feel free to reach out to me through Twitter or Mastodon. My handle is peterzoot118, and on Mastodon at ruby.social. Or through email. My email is peter@peterzoot.ca. Thank you for listening to my talk.
Thank you so much, Peter, for presenting the talk. I'm sure people, if you have questions,
Yeah, you can ask them now.
feel free to ask if you want to ask them now, or we, I'll handle the chat. I just wanted to give a shout out to all of you guys again for coming. Obviously, we have a website. We've got a newsletter. So when I've got the next event ready to roll, I typically send out a newsletter. So if you're not on that mailing list already, please sign up. We'd love to have you. I promise we won't spam you. We're also on Twitter at Toronto_Ruby. And I tweet a little bit when we have the events and stuff like that. But other than that, thank you so much for coming. And if you have any questions, or if you are just joining us, on the name tags there should be some stickers. And some folks have a yellow sticker that means they're hiring. And if somebody has a blue sticker, it means that they're looking for a job. So if you're hiring, then you can find those people. So I'll leave it for questions.
Yes.
So you have tuning A, B, C, right?
Yes.
Is it possible that tuning A and B or C could affect each other? Like,
So that is a concern. That is an actual concern. But Ruby's configuration mostly, so the tuning parameters inside of Ruby are actually mostly, I would say, mutually exclusive. So they don't actually affect one another much. So usually you don't run into a case where because of something, you run into a local maxima instead of a global maxima or a minima, depending on how you want to see performance improvement or time spent. You usually don't run into those situations where you run into that kind of problems. So it's not. It could happen, but it's not very likely. But if you do think you're running into that kind of problem, just remove one from the experimental group and see if it makes it better or worse. Yes.
Would you be able to talk to, and I'm trying to figure out how all these things fit together, but your work on the garbage collection as it relates to like the compiler that was introduced in Ruby 3.2? Logit? Is that how you say that?
So there's a lot of parts in Ruby, right? So we first when you see source code in Ruby, there's many phases. First, it gets parsed into this thing called the abstract syntax tree, the AST. And then the Ruby converts it into bytecode called YARV, which stands for Yet Another Ruby VM. And that was introduced in Ruby 1.9 because previously it didn't have, not very important, but previously Ruby used to be a AST walking interpreter. So it would take that abstract syntax tree, which is exactly as you think of it, it's a tree. So you have like an if statement, you have the body, you have the condition, the body, the contents in the if statement. So then it's basically a tree, and we'll walk that tree to run your Ruby program. In Ruby 1.9, that changed to be a bytecode interpreter, which means that after you convert, you get the abstract syntax tree, you get a list of instructions. And a sequential list of instructions, just like your CPU instructions, except it's Ruby instructions for the Ruby VM. So once you have those list of instructions, these instructions do things, and certain things allocate objects. For example, if you do object.new, it calls the new method on the object class. And that allocates an object. The new method allocates an object. And that's where the Ruby garbage collector comes in. So the VM asks the garbage collector, hey, can you give me an object? And the garbage collector allocates an object and hands it to the VM, the virtual machine. But if it doesn't have any slots, then that pause to ask for an object would last much longer because it runs a garbage collection cycle before it allocates an object. So there are many parts, and you were talking about YJIT, which is a just-in-time compiler for Ruby. And what a just-in-time compiler does is it looks at the list of your Ruby instructions that you have that was generated for yard. And let's say let's say you have a method a and b that accepts two parameters a and b, and then in the method you just do a plus b. Very simple, right? But in Ruby, that could mean anything. A could be a string, b could be another string, or b could be an integer. And if you try to do a string plus an integer, then it won't be very happy. It'll say type error. But so then the Ruby VM has to generate generic instructions. Whereas if you did something known like 1 plus 1, then you know that these are numbers, and you can just you can simply add them. You know the plus operation means add them. So what YJIT does is, for the case where you don't know what A and B are, it can say that, hey, during runtime, I see that you often pass numbers, integers for A and B, so let me generate this specialized set of instructions just for integers. So if I see that A and B were both integers, then I run this very special set of instructions that are significantly faster, because that code assumes that A and B are both integers, and you can just directly add them. So those are how the various parts of Ruby play together in a high level kind of way.
So if I'm understanding correctly, the work that you're doing on the allocation lists, the variable allocation lists, would be run regardless of whether it's YJIT or MJIT that was
Yes.
compiled?
Yes, yeah, because the garbage collector is kind of its separate thing.
Yeah.
So the garbage collector actually can't really look at your Ruby code.
Yeah.
It does a little bit, but that's the
That's awesome.
that's why it's Ruby's garbage collector, not generic garbage collector. But for the most part, it's a separate kind of thing that has no idea. The VM says, hey, allocate me an object, allocate me a regex, allocate me a hash, and the garbage collector goes, okay, here you go. Yes.
So this is about like tuning production. Is there anything for like tuning developer machines? With, like, I know Shopify probably has like an internal thing for running Rails and stuff like that. Is there anything that's given like tuning parameters for developers in that kind of degree?
For developers, like a
Do they just
developer.
max everything out and give too many slots, or do they just hand them prods config and say, okay, that's on your machine for tuning the GC?
Yeah, so we're mostly not very concerned with development performance,
Sure.
because it's not that bad. Like, as a developer, if your request takes 2 seconds instead of 200 milliseconds, kind of sucks, but it's not the end of the world.
So do you think devs are just taking the default config? Basically?
Yeah, and Ruby's default is a very sensible list of configurations for the garbage collector. So, you know, we spend time messing with the production stuff, because improving by 10% means that we save a lot of money every year and improve experiences, which drives increase in revenue. We do work on making sure that, you know, tests run fast, tests are not flaky, and stuff like that, but we don't like optimize like, oh, we got 10% lower response times in development. Like, we're like, okay, well, it's probably not a super good use of developer time kind of thing.
Sure.
Yeah.
Can you explain why the compaction feature is disabled by default, and also like what you might consider avoiding?
Yeah, so compaction was introduced in Ruby 2.7, I believe. And so it means that a lot of code don't play well with compaction, because before that, no objects moved, ever. So, you know, it just doesn't move. So now that suddenly objects move, there's a lot of things that don't work well. And we've been putting a lot of effort in getting not just Ruby itself safe for compaction, but all of the surrounding gems. Because we have so many gems that are written in, like, that are native gems written in C, C++, and now Rust. And those things all have to be compaction safe. They either have to support it or they have to do this thing called pinning, which I'm not going to get into, which says, hey, I know I don't support it, so please don't move this. So if they don't do one of these two, then they're in for trouble. And so that's why it's not enabled by default. And another reason is that it makes major garbage collection cycles even slower, because now it has to move objects around and not just mark and then reclaim. It has to mark, move, and then reclaim. So then the major garbage collection cycles actually end up taking much longer. And so that's why it's not enabled by default.
In Shopify, are you running compaction?
Yes, we are. Because of the significant improvement in copy on write performance. So we end up, so every time we fork into another unicorn process, we save a lot of memory. And so then that's why we do it. And we also see performance improvements, memory improvements and performance improvements. So yes, we run compaction at Shopify.
Sorry.
Yeah.
I mean, but are the negative effects of enabling compaction obvious, or is it you expect a certain number to be regulatory and you're seeing a different number?
So it would make major garbage collection cycles slower, and usually major garbage collection cycles would affect things extremes like 99th percentile and 99.9th percentile. Those might become worse, and those might become significantly worse, depending on what kind of objects are in your system. Sorry, there was one at the back.
If I understand you correct, so the smartest Ruby engineers in Shopify were able to increase the request time by 10%. So based on this, at which point of the application, which scale you should think about the garbage collection tuning? Because
Tuning?
it's not the most memory you use, yeah? It's probably because something was open connections or database.
Yeah, so we looked at the proportion of time spent inside of the garbage collector, and we saw there was a good room for improvement. I don't remember what the specific number was, but it's definitely the double digits of percent time, especially on the extremes like 99th or 99.9th percentile, where we actually do spend seconds in time in the request. And so if we can shave off seconds from the request, then it makes these extremes much better experiences for the user. So really, like tuning the garbage collector, it's like, is it a problem? Is it a problem? Are you trying to optimize for the best response times? If it is, then you should look into it. If it's not, then probably not, because the defaults in Ruby are sensible numbers. They're things that make sense for a wide variety of apps, so including Rails apps. So maybe you shouldn't mess with it if response time isn't a concern, response time isn't something you're going to heavily invest engineering effort into trying to improve. Does that make sense?
A lot of those metrics sound like they're fairly straightforward too, so it's not, correct me if I'm wrong, but does it sound like you're doing a 12-month research project on how to tweak the numbers? It sounds like they're relatively sane to work with.
Yeah, so it's designed to be, easy to work with, but sometimes it's tricky because you don't know what they're doing.
Sure.
And so it's sort of a black box. There's this configuration that you have to do, but you don't know what it really does on the inside. And it is time consuming in the sense that every time I apply a tuning variable, I have to wait several days to gather enough results so that I know that when there's low traffic, it works well. When there's high traffic, it works well. When on the weekend there is like no deploys for 2 days, it's not going to linearly increase in memory usage and cause our workers to run out of memory. So all of those things, that's why it ends up taking so long. That's why something like tuning storefront renderer took like maybe 3 or 4 months, because every time I apply something, I'm like, okay, now I have to wait like a week to gather enough data, and then I have to analyze this data, and then I have to do some sort of action based on the data. So then it ends up becoming time consuming in that sense.
Would be fair to say that it's calendar time intensive,
Yes.
but not necessarily hours time intensive.
Yeah, yeah, I would say so, especially if you use AutoTuner.
How to address that issue? The thing is, this could be a low-hanging fruit.
Yes.
Could
Yeah.
be.
Yeah. Yes.
I just wanted to clarify, you mentioned that some gems don't play nice with compaction. Would you experience like sec faults or anything? Or
Yes.
would run?
Oh, all the time.
Okay.
All the time. Oh, like that's one of the responsibilities of our team is to look at crashes that happen in production. We turn on compaction and there'll be an explosion of crashes that happen in production. Do things like cause production incidents, all sorts of good stuff like that. Oh yeah, all the good
And these
stuff.
only pop up in production. You don't turn it on in something else before.
Oh, we turn it on. Oh, we get so much in CI. And then we fix all of the ones in CI.
And then you still
CI
get
is
more
great.
in
And then you get
production.
more in production.
Oh my god.
What are these gems doing that's not happy with compaction?
It's because of legacy reasons. It's because Ruby 2.7 introduced compaction, and before then, no objects moved.
What was the change that resulted in objects moving?
Compaction. It's a feature.
Oh,
It's a
okay.
feature. So
So the gems, the legacy code is making assumptions about objects not moving, and
yeah,
any of the
and there's
compaction breakdowns.
still new code that assumes that objects do not move. So because it's not enabled by default, so unless you test with it, then you might not find a problem.
Little chicken or egg situation.
Yeah.
So let's just do maybe a couple more questions, and then we can all mingle and stuff.
Yes.
Got a question, because you got a lot of experience running like a large production environment. Of the allocations you see during a request, how many are gone by the end of the request?
Ideally, all of it.
Yeah, so then why isn't there an allocation strategy built around that?
Because not everything does.
Yeah, so that's what I mean, like what doesn't?
Let's say we only flush our buffer for logging once every so often. That lives past the request. Buffer things, or just things bad developers do and just gets left out. or like even like in request, like when you boot up, things are lazily initialized when you first use it. So during the first request after boot up, there might be things that linger on for the remaining lifetime of the app.
Right, it's almost like if there was like you have these young and old objects. If there's another one that's just like request bubble.
Right.
When you close out the request, you can move those into the other buckets. With that.
So there is some that would need to we need to have a guarantee that objects do not spill out into the global state in a particular request in order to make it so that it is safe to say this chunk of objects that are allocated to a request we can just immediately throw out after the request. So in order to do that, you have to have guarantees that those objects do not spill out into the global state. And right now, there is not really a way to do that in Ruby. So there is a little bit of talk, but not really much work going into. So Raptors does sort of give that guarantee in that you can guarantee that objects created within the Raptor cannot be used outside of the Raptor unless you specifically pass it outside of the Raptor or to another Raptor. And so that can be used, that can be taken advantage of to guarantee that objects created in the request do not spill out into the global state. But there is currently little to no effort into developing a feature like that.
It's a cool feature, I just haven't seen anybody use it.
Yeah, so it is still very much in the experimental stage, Raptors, and in that a lot of things do not work that well, and performance isn't great, a lot of things crash, and it is still difficult to use because of the passing around mechanism that is implemented. Yes?
Yeah, thank you, Peter, for the great talk and for all your work on Ruby. So, question is, you are basically optimizing on a Ruby heap,
Yep.
but how we can compare that to the heap of heap, where the large objects are linked? So they are allocated with whatever allocator is set, malloc or whatever, GA malloc, how maybe fragmented could be that heap, and does that cause any performance penalties comparing to Ruby heap?
Right. So there are different malloc implementations, and the characteristics change significantly depending on the malloc implementation. So malloc is a very simple API where you just say, I want 100 bytes of memory, it gives you 100 bytes of memory, and then once you're done using it, you pass it to this function called free, which releases the memory back to the system. But the implementation inside of malloc is actually very different depending on what type of malloc you're using. So whether you're using glibc, that ships with many Ubuntu distributions, like many Linux distributions like Ubuntu, or you're using another malloc implementation like JE-malloc. So malloc itself is basically a black box to us. So we can't really do much with malloc except reduce the number of malloc calls. We can't say this particular sequence of allocations is better for malloc, or like how can we optimize our app for malloc. We can't really do that. The only thing we can do is do less. So that's exactly what variable width allocation attempts to do, is by making the slot sizes variable in size, you can reduce dependence on malloc.
Thank you.
I think we're good. Thank you so much for joining us. Yeah, thank you guys for coming out, and yeah, hope you hang around. We've got the space until what time? Until 9? Okay, so I will keep everybody on track. About 50 minutes to mingle.